Look around you, take a moment. In your pocket, on your wrist, on your desk, they are everywhere. These silent, glowing rectangles have become extensions of our minds, our memories, our very selves. We use them to talk to loved ones across oceans, to navigate strange city streets, to capture fleeting moments of beauty, to ask the universe any question we can imagine. These devices, our classical computers, are the architects of the modern world. They are so woven into the fabric of our daily existence that we often forget they are there, working tirelessly, calculating, connecting us all in a vast digital tapestry that spans the globe. They are the bedrock of our civilization. These machines are our portals to immense libraries of knowledge, our tools for creation, our windows into distant worlds. From the simple act of sending a message, to the complex orchestration of global financial markets, they are the quiet collaborators in almost every human endeavor, from the artist's studio to the scientist's laboratory. But have you ever stopped to wonder how they actually work? Imagine a long hallway lined with billions of light switches. Each switch can only be in one of two positions, on/off. This is the fundamental world of a classical computer. It's a world of black and white, yes or no, 1 or 0. This simple two-state system is called a bit, short for binary digit. Every single thing your computer does, every photo you see, every song you hear, every word you read, is ultimately translated into an incredibly long sequence of these ones and zeros. It's a universal code, a language of absolute states that machines can understand perfectly. Your computer's processor is a master of manipulating these bits at unimaginable speeds. It's like a fantastically fast mail sorter, looking at each bit, and based on a set of instructions, deciding whether to flip it, leave it, combine it with another. It performs simple logical operations, but it does them billions of times per second. To store the letter A, for instance, the computer might use a specific pattern of 8 bits, like 01000001. A picture is just a grid of millions of such patterns, each describing the color of a single pixel. This binary approach has been spectacularly successful, but it has its limits. Now let's leave the familiar hallway of on or off light switches and enter a much stranger, much more wondrous place, the quantum realm. This is the world of the atom, of the electron, of light itself. Down here, the rules of our everyday experience break down. Things are no longer just on or off here or there, they can be a little bit of both all at the same time. A quantum computer harnesses this bizarre and beautiful nature of reality to perform calculations in a fundamentally new way. It doesn't just process information, it embodies a deeper layer of the cosmos. Instead of a bit, the quantum computer uses a qubit or quantum bit. Think of our light switch again. In the classical world, it's either on or off, but a quantum switch is more like a dimmer. It can be fully on, a 1, fully off, a 0, or, and this is the revolutionary idea, it can be any combination of on and off simultaneously. It exists in a superposition of states. This ability to be in multiple states at once is what gives the quantum computer its incredible power. Let's dive deeper into this idea of superposition. It's one of the cornerstones of quantum mechanics. It's what makes a qubit so special. Imagine you spin a coin. While it's in the air, spinning and tumbling, what is it? Heads, tails? In a way, it's neither and both. It has the potential to be either, and its final state is only decided when it lands and you look at it. A qubit in superposition is like that spinning coin. It exists in a cloud of probabilities, a rich mixture of 0 and 1. Only when we measure it, when we look at it, does it collapse into a definite state, either 0 or 1. This may sound abstract, but it's the key to unlocking immense computational power. Because a single qubit can represent both 0 and 1, a system of qubits can explore a vast number of possibilities all at once. Think of it like a painter with a limited palette. A classical painter can only put one color on the canvas at a time. A quantum painter can apply all the colors simultaneously. The final masterpiece only reveals itself at the end, but the process involved every possibility from the very beginning. This parallelism is a fundamental feature of how our universe works at its smallest scales. By controlling this delicate state of in-betweenness, we are preparing to solve problems that were once considered forever beyond our reach, using the universe's own hidden computational power. As if superposition weren't strange enough, the quantum realm has another trick up its sleeve, a phenomenon so bizarre that Albert Einstein famously called it spooky action at a distance. This is entanglement. Imagine you have two of our quantum coins and you entangle them. This means you link their fates in a special quantum way. Now you give one coin to a friend and fly to the other side of the galaxy. The moment you look at your coin and see that it has landed on heads, you know, instantly, that your friend's coin has landed on tails. Always. Without exception. This connection feels instantaneous, faster than the speed of light. It's as if the two coins, no matter how far apart, remain a single system. They are no longer independent entities. Their destinies are intertwined. Measuring one instantly affects the other. This doesn't mean we are sending information faster than light. The outcome is still random, but it reveals a deep, non-local connection woven into the fabric of space-time. It's a property of reality that our classical intuition struggles to grasp, but one that quantum computers can use to their tremendous advantage. In a quantum computer, entanglement acts as a force multiplier for the power of superposition. It creates intricate correlations between qubits, like having a team of problem solvers who coordinate their search with perfect, silent efficiency. So we have these qubits, existing in superpositions linked by entanglement. What does this actually let us do? It gives us what scientists call quantum advantage, the ability to solve certain types of problems that are practically impossible for even the most powerful classical supercomputers on Earth. These aren't just problems that are a little bit harder, they are problems whose complexity grows so fast a classical computer would need longer than the age of the universe to solve them. For these specific tasks, a quantum computer isn't just faster, it's playing a different game entirely. One of the most famous examples is factoring large numbers. For a classical computer, this is an incredibly difficult task. It's the basis for much of modern cryptography. It keeps your credit card information and secret messages safe online. In 1994, mathematician Peter Shor developed a quantum algorithm that could find these factors exponentially faster. A sufficiently powerful quantum computer could, in principle, break many of the encryption codes we rely on today. But the power of quantum computers extends far beyond code breaking. Their real strength lies in simulating nature itself. The universe, at its most fundamental level, is quantum mechanical. A quantum computer, because it operates on the same quantum principles, can simulate nature with perfect fidelity. It speaks the universe's native language. Let's step aboard our ship of the imagination and journey into a future powered by quantum computation. What will this world look like? In medicine, the change could be revolutionary. Quantum computers could simulate how a new drug interacts with proteins in our body with perfect accuracy. This would allow us to design personalized medicines tailored to an individual's unique genetic makeup, fighting diseases like cancer, Alzheimer's, with unprecedented precision and minimal side effects. We could discover new antibiotics to combat resistant superbugs. In materials science, the possibilities are equally staggering. We could design room-temperature superconductors, materials that conduct electricity with zero resistance. This would transform our energy grid, leading to perfectly efficient power transmission, ushering in an age of ultra-fast magnetic levitation trains, powerful compact motors. We could invent new catalysts to make industrial processes dramatically more efficient, like the production of fertilizer, saving immense amounts of energy and reducing our impact on the planet. We could design materials that pull carbon from the atmosphere, directly helping us combat climate change. Our ability to understand the world would take a quantum leap forward. Complex systems, global financial markets, Earth's climate, could be modeled with a new level of detail. Building a functional large-scale quantum computer is one of the greatest scientific and engineering challenges of our time. The quantum world is incredibly fragile. A qubit in its delicate state of superposition is like a soap bubble. The slightest disturbance from the outside world can cause it to pop. This decoherence, as physicists call it, is the arch-nemesis of the quantum computer. A stray vibration, a tiny fluctuation in temperature, a stray electromagnetic field can destroy the quantum computation, causing the qubits to collapse into boring old classical bits of 1 or 0. To protect these fragile qubits, scientists have to go to extraordinary lengths. Many quantum computers must be housed in special dilution refrigerators, complex machines that cool the quantum chips to temperatures colder than deep space, just a fraction of a degree above absolute zero. This extreme cold minimizes thermal vibrations, helping the qubits maintain their quantum states for longer. They are also shielded in layers of exotic metals to block out the Earth's magnetic field and any stray radio waves. Building a quantum computer is like creating a tiny, ultra-quiet, ultra-cold pocket of the universe where the laws of quantum mechanics can be put to work. Another huge challenge is controlling the qubits and making them talk to each other. Despite these hurdles, progress is astonishingly rapid. Researchers around the world are experimenting with many different ways to build qubits. We are learning how to tame the quantum world, one qubit at a time. We stand at a remarkable moment in human history. For millennia, we have looked up at the stars and out at the world and tried to understand its rules. We discovered the laws of motion, gravity, electromagnetism. Then in the 20th century, we peered deep inside the atom and discovered the strange and wonderful laws of quantum mechanics. For 100 years these laws have described the world, but we have been observers. Now, for the first time, we are learning not just to observe the quantum world, but to harness it, to build with it, to compute with it. The journey ahead is long and filled with challenges we can't yet foresee. There will be dead ends, false starts, and moments of profound difficulty. Building a universal, fault-tolerant quantum computer may take decades, but the quest itself will drive discovery. It will inspire a new generation of scientists and thinkers to ask bigger, bolder questions about the nature of reality and our place within it. The adventure is just beginning.